So first of all, you should put in your attendances now. And as you can see that I have a couple of things to share with you before beginning this class. So first of all, I have so for this year I have decided for those of you who would later be interested in doing project with me, make sure before you approach me, you read this paper. Okay, so if you search in Google with this thing, then it will just lead you to the paper. It says quantum interference with slits. So how what do you have to do? So you have to read this carefully. So this thing is about so this thing breaks your say intuitive idea that uh, interference and diffraction phenomena like that which light undergo, they are a consequence of wave nature of light. Okay, and we can explain this well with the wave theory, which is of course true. But using quantum mechanics, how would you explain interference and diffraction and some mathematical idea to get the same formula of interference and diffraction using quantum mechanics? So first you have to read that, understand that to your best of your extent, and then send a 2 or 3 page summary of your understanding, what you understand by that. If you want, you can include calculations into that also. And what do you think about that? How that idea can be extended? What new things can be done from there? There is no right or wrong answer. I just want to check your approaches to new things, like things that you are not used to. Okay, and that is very important for me. So people who are interested in doing work with me, so I want to check your approaches to new things. So your marks or anything on this classical mechanics course will not depend on this. Whether you do this or not, it's completely up to you. But people who would later be approaching me for project, make sure you do that before approaching me, and send me by email a write up of say a couple of pages what you understood by this thing. All right. So now the second comment I have here is in I was just browsing through some of your submissions in the for the homework, and some people mm, do things like this. So for a partial differentiation, uh, so if f equals f qt, then they write steps like this. So del f del t over del q del t, somehow they cancel this dt and dt, and then write del f del q. No, this is wrong. This doesn't work in partial differentiation. So there are many such mistakes that I pointed out. So remember, partial differentiation is something else compared to total derivative. So if you uh, do steps like that at the end, even if your answer is correct, you get zero. Okay, there is no consideration about these kind of things. Okay. So make sure you understand partial derivative very well, and do not make these kind of mistakes. So you do not get any credit for writing the correct answer. There is no absolutely no credit unless your steps are correct and your arguments are foolproof. Okay. So if things like these are in between, then there is no credit. Okay. All right. So those were two minor comments that I wanted to share with you. Uh, I hope it is clear to everyone. And if there are some questions about these 2 points, you can ask me now. Okay.
Sir, we have to submit the writings within 10 days.
This writing? No, no, no,
Yes,
no,
sir.
no. You take 2 months just
Okay, sir.
before.
Okay,
I
sir.
mean, at the end of the semester, not 10 days. Okay. So you
Okay,
read.
sir.
This will take time. Okay. So that's why I want to see the approach. You take your time. You understand. uh, and just before after the semester ends you would be I think the DPGC physics will contact you regarding seminar topics and that. So before that you have to submit, not 10 days. Okay.
Okay, sir.
So you take the whole semester.
Hmm.
Okay.
Okay, sir.
Good. Uh, okay. Any other questions? Maybe from earlier classes?
Sir, what are the topics on which you done the project of your project work?
I will
This
probably float only one project, and I have not decided the title yet or the theme yet. But it would
no, but
be.
which area?
Oh, you can check my webpage. I work in theoretical particle physics, so it would be related to that. Okay. No,
Okay,
theoretical particle physics or quantum field theory, things like that. Okay.
okay,
So,
sir.
yeah, good. Now, uh, let me continue. So, in the last class, what we left were the discussion of Noether's theorem. So, So the essential idea behind this Noether's theorem, as I stated in my last class, was that the Lagrange's equation can be rewritten in this form. So dpk dt is equals minus del L, sorry, plus perhaps del qk, right? So I called this thing my generalized momentum. So this is del L del qk dot, which I call my generalized momentum, and this was my generalized force. And our conclusion was that if del L del qk equals 0, so the statement was if L doesn't depend explicitly on qk. This statement also comes in all different varieties. Sometimes you will see statements like if qk is a cyclic coordinate, then or all of these leads to del L del qk equals 0. Then it implies that pk is conserved. Uh, so as to say dpk dt equals 0. So this is the this is the statement in classical mechanics by which we usually know the Noether's theorem. And uh, I tried to give you an idea that this statement is very powerful in a sense that this del L del qk equals 0. If L does not depend on qk explicitly, then this L is invariant. So L doesn't change if qk is shifted to say qk plus epsilon. Okay, uh, so that means there is a translational symmetry along qk. So there is a translational. So the translational is let me not call a translational symmetry. Let me say there is a shift symmetry. So if you shift qk by qk plus epsilon, so shift symmetry uh, along the kth direction. Okay. Now, this shift symmetry comes in all possible varieties. So this if this qk is a physical coordinate like x, y, and z, then this shift symmetry is basically translational symmetry. It's a physical translation along the physical coordinate. So if qk is say any coordinate, uh, then this shift symmetry I call it translational symmetry. let's say. And if it is associated with rotation, so remember in the two-dimensional polar case, I said that theta is one of my coordinate. And if you change theta to theta plus epsilon, if qk is equivalent to theta, then it is equivalent to a rotation. So this gives you a rotational symmetry. Okay. So you see, uh, if my translational symmetry is the symmetry of my Lagrangian, then the generalized momentum for translational symmetry is the usual linear momentum. Okay, and the generalized momentum corresponding to this rotational degree of freedom is your angular momentum. Okay. So the statement that the translational that the translational symmetry leads to a conservation of linear momentum and rotational symmetry leads to a conservation of angular momentum. And in general, any kind of shift symmetry along any of the coordinates leads to the generalized momentum being conserved. Okay. So in our old days, we used to think, why is linear momentum conserved? So linear momentum was conserved because of linear momentum was conserved because of there is no force acting on the system, and angular momentum was conserved because there is no torque associated with the system, or there is no torque working on the acting on the system. Now we learn to see beyond forces and torques. Okay, so this is a very powerful statement. So what I have learned here, so the lesson we got here, so look beyond forces and torques. Okay, so the essential idea is that now you will say, why is your linear momentum is conserved? You say there is a translational symmetry in the system. Why is your angular momentum is conserved? Because there is a rotational symmetry in the system. And why is anything even is conserved? Because there is some kind of symmetry in the system. So this is a general statement that I am leading towards, that we will be working in. So that is the language we will be working in. So the general principle, so we will not care about forces and torques anymore. Okay, to get an idea. So remember, our problem of finding the working principle or working dynamics of more complicated system, like systems of fundamental particles, let's say, or more complicated problem where your intuition is not working. Let's say uh, the interaction between a neutron and a proton. Okay, how would you write that? Okay, so what is the force? So you are always used to think in terms of force and torques. So to describe the dynamics of a system, you need to know all the forces and all the torques that are working on the system. Okay, now we have created a language where the information about forces and torques are not necessary as long as we can guess the symmetry of the system. Okay, so that is the thing that I am trying to give the message. So if I say study nuclear physics, I study the dynamics of proton and neutron, I would be stuck because I do not know the force working between a proton and a neutron, the exact functional form of that force I do not know. But the Lagrangian formalism tells me now that there is a way to understand the dynamics of a complicated system even if you do not know the forces and torques acting on the system. Okay, I will come to more examples because of that. But make sure you understand Noether's theorem very well before you proceed. Okay? And if you do not understand it, ask me questions. Now, I will proceed to kind of derive a more general form of the Noether's theorem. So, uh, as you will find, the Noether's theorem is not just limited to this kind of shift symmetry. So this is one particular way of uh, um, handling symmetries. Okay, And then, so suppose there is a system, uh, so there is a system, so L is equals, so a system is described by this, and this Lagrangian is invariant. I should not say invariant, but it's kind of equivalently transported, or like it differs by a total derivative of a function. If you change your qk to, let me say, qk plus epsilon, I do not write fk because I use this. So let me call jk q. So this q means it depends on all the q's. Okay. So the idea I am trying to convey here, that this Lagrangian is invariant under that transformation. Okay. So if you change qk to this, then the Lagrangian is invariant. So Lagrangian is invariant under this transformation. So if you make these changes, then nothing happens to the Lagrangian. Yes.
So this xi k q, does it mean that this xi k is depending on all the coordinates, like q k, k is from like 1 to whatever the
Yes,
number is?
yes, precisely. That q without any label means that jk can depend, in general, depend all the coordinates. Okay.
Like all the coordinates simultaneously, or like just one of them?
No, all the coordinates simultaneously. If you like, you just put a subscript I there. This I is different from k. Okay.
Okay.
So that means that this jk is, so the index k means you have different functional form of xi for different k's. Okay. And in general, each of those xi's depend on all the other coordinates. Does it make it clear?
Yes, sir.
All right, good. So and of course, I am working in the limit that epsilon tends to 0. Okay. Now you will see there would be complicated systems here. There will be, for example, if you're, I said that the symmetry is of this sort. Okay. The symmetry is like this. Okay. But there can be more complicated symmetries here. So for example, if you're Lagrangian, let me give you one Lagrangian here example. Say Lagrangian is half m1 x, say x dot square plus half m2 uh, y dot square minus 2x uh, plus y, let's say. Okay. So you can identify kind of, if you want, you can identify this is your kinetic energy and this is your potential energy Vxy. Now you will see that this is invariant if you change, say, x to x plus, say, epsilon, and y to y minus 2 epsilon. Okay. So so this is the thing. So now you see that under the so 2x plus y is remains unchanged. Okay. And of course, if since this is a shift symmetry here, then x dot equals x dot and y dot equals y dot. So the kinetic energy part also remains like this. But what does it imply for this xi k? So if you call x to be your q1, okay, so that means is q1 times epsilon into 1. So this is your xi1 q, and if you call y to be your q2, then this is so this xi2 q will be minus 2. So here you have xi1q equals 1 and xi2q equals -2. So you understand what I am trying to tell here? Okay. So, and in general, these can depend on other q's, let's say for more complicated problems here. Okay. Now, the idea is if that is the symmetry of the Lagrangian, then the first order change in Lagrangian would be 0. So, suppose then under this transformation, L would be changing to L plus dl d epsilon into epsilon. Okay, the first order change is that. So because of this transformation in Q's, L will be changed by this, let's say. So if I say that L does not change, then that means the first order derivative, this del L as a dl d epsilon is 0. Okay. So if you for the Lagrangian to be invariant, I claim that dl d epsilon should be equals to 0. Okay. So remember that L is a function of q dot and t, and the dependence on epsilon is only contained in q and q dot. So you can now try to evaluate what is the value of this dl d epsilon. Okay. So this dl d epsilon would be given by say summation over k, okay, del L del qk into del qk del epsilon, the chain rules of partial derivative, okay, plus del L del qk dot times del qk dot del epsilon. So this follows from the chain rule of partial derivatives. So now I have to determine these first of all I will determine these two things. So del qk del epsilon and del qk dot del epsilon. So first of all I notice that qk is basically qk is being, say, let's say, changing to qk plus epsilon times xi kq, and so quite evidently qk dot would be given by qk dot plus epsilon times so epsilon times d xi k dt. This is the total derivative of that thing. Okay, so whatever that is, you just you can break it apart, but for essential purposes, this is this. So clearly from here I can write del qk del epsilon is equals xi k, and from here you can write del qk dot del epsilon equals d xi k dt. All right. So what you have here, let me use a different, so I can write here xi k, and this one is d xi k dt. So these two terms are just this. Now another thing is that you can use Lagrange's equation to replace this. So what is del L del qk? From Lagrange's equation, this term can be written as d dt of del L del qk dot, right? So just from using the Lagrange's equation. All right. Now notice what is happening here. So d dt of del L del qk dot times xi k, and del L del qk dot times d dt of xi k. So if you notice this is the product rule of total derivatives. Okay, so you can write this thing as summation over k, let's say d dt of del L del qk dot into xi k q, this, right? So that so the first term, if you take the product, the first term is precisely this, and the second term is actually here, this one. Or I can take out the derivative part, so d dt of summation over k del qk dot to this thing, so d dt of this. Now if this is a symmetry of the Lagrangian, then I have already found that dl d epsilon equals to 0. That means this should be equals to 0. What it implies is that the thing within the bracket, so this now I call, say, p. Okay, so and it can be in general a function of q and q dot. Okay, uh, running over all the index. So I can write down then dp dt equals 0, or p is conserved. Okay, so what is the expression for this key? So p is del L del qk dot times xi kq. So this is the general form of conserved momentum. So this is the general structure. So this is the general structure of the conserved momentum. Okay. So where you have the general values of this psi kq. Now you can check that it reduces to the usual momentum for a shift symmetry. Okay. So for a shift symmetry, so for a shift symmetry along, say, ith direction, so the symmetry would be given by qy equals qy plus epsilon. So I am considering shift symmetry only in the ith direction, nothing else. Okay. So that means xi I equals 1 and all the other xi k equals 0. So for k not equals I, you have all the xi k's to be 0. Okay. So if you plug this in this expression, then this p becomes, so the summation over k drops out because only I survives. Okay. So instead of writing delta xi I equals 1, you can also write it to be, say, delta ki. That means for for k equals I, it is 1, and for k not equals to I is 0. So if you replace xi k to be delta ki here, so only the ith term survives, and it is del L del Q I dot, which is your generalized momentum corresponding to Qy. Okay, so I recover the usual form also using this general structure of the Noether's theorem. So what does Noether theorem tell you here? So Noether theorem tells you that for each symmetry of the Lagrangian, there is a conserved quantity. Okay, so so let me see. So for each symmetry of the Lagrangian, there is a conserved quantity. So if you can somehow guess the symmetry of the Lagrangian, then you can then that symmetry will lead to what quantities would be conserved in the system. Okay, and this is a very powerful statement that we would be using again and again in our upcoming lectures. Okay, so this is the general form of the Noether's theorem, like general form in classical mechanics, I might say. like point particle mechanics, it would be differing slightly in the case of classical field theory and then to quantum field theory. But this is the version of Noether's theorem for classical mechanics, for classical mechanics, for point particle mechanics that we are now focusing in. So I will pause for a moment here. I can guess that this might be a bit new to you, so you might have questions. So if you have, ask me.
Sir, just one doubt. The xi k which we chose, with assumed it to be a function of q only, the qi or the coordinates. Can it
Yes.
be a function of like qi dot, like the first derivative, or the time essentially, if we say explicitly?
No, if it is a function of q, if it is a function of q dot, then this will not work. You will see that in the derivation of the Noether's theorem, I have used the fact that xi k only depends on q, and that's
Yes,
why
sir.
I could write that thing. But that's why it's not a function of q dot. Okay, that's the first point. The second point, in this part of the classical mechanics, xi k, so it's a very dicey statement. Okay, so I would not say that JIK does not depend on T. So since I am doing non-relativistic classical mechanics, you see that the coordinate and moment, the coordinate and time, the space coordinate and the time coordinate are treated differently. Okay, so we take all the derivatives with respect to time. Okay, there is no kind of space derivatives. So the space derivatives are not treated on the equal footing of the time derivative. But when you go to the relativistic version of this classical mechanics, which is classical field theory, hopefully I will come to that, then t just becomes one of the coordinates, right? Just like x, y, z. And in that scenario, so this ik can depend on everything.
Yes, sir.
Okay. Anything else?
So here L by the transformation, that Q Q plus epsilon xi k,
Yes.
from that L tends to means L becomes L plus epsilon dl d epsilon.
Yes.
This is this the Taylor expansion of that L
Yes.
equals to L? Okay.
Yes. This is the Taylor expansion. So I am
Okay.
expanding about epsilon, and I am claiming that L will not change. So you will have L equals L. So the first order derivative should vanish.
Okay.
Okay. Any more? All right. So I hope you got the gist of it, but do read it mm, carefully and try and understand it very well, so that you have a better feeling of what message I'm trying to say. By the way, just one comment is that for last year teaching, I prepared a handwritten note for this course, and I have made that available on my IIT Indore website. So if some of you are interested, you can also check that out. But I would always suggest go through the textbooks because those are always better. But if you are interested, perhaps some of you have already discovered that, but if there is someone who did not know about this, just to let you know that the materials that I prepared for last year teaching, I just made it public. All right. So now, let's say, so I am for a long time I am preaching that symmetries are useful. Okay. And of course they are, and from symmetries we can guess so many things. And these symmetries. So, for example, let's say, uh, let's say Newton's first law. So the Newton's first law. So what it says, that no force and then linear momentum is conserved. Essentially this. Yeah. Now you might say that all this big talking that I did with symmetry, that we already knew Newton's first law, and we know that when there is no force, then the linear momentum is conserved. And I said that sometimes to understand the dynamics of a particle, the information of force is not necessary. So you might say, can I arrive at Newton's first law without talking about force? Okay. And to give you the first glimpse of symmetry, I will do just that. By the way, this is not a proof of Newton's first law. It cannot be proved. But what I'm trying to do here is that if we did not know anything, okay, suppose we are born before Newton was born, the Galilean time, and we are trying to devise how a free particle will move in space, then the most natural law that we have obtained um, uh, is the Newton's first law, actually. So how to do that? So I will, for simplicity, I will consider motion in one dimension. So I just say that a free particle moving in one dimension. So let me consider, this is my system. So a free particle moving in 1D. Now, if a particle moves in one dimension, if you know nothing about this, what is the minimum thing that you can say? So, if there is nothing to distinguish, so you have perhaps. So, what I am trying to do, I need to describe the system. Okay. So, I need to guess a Lagrangian that depends in general on x, x dot, and t, and I am trying to guess that. All right. So, the idea, first of all, is that um, there is no preferred choice of origin. So it has a symmetry, like space is homogeneous. We just say, so the technical term for that is that space is homogeneous. That means every point in space is treated with equal footing. Okay. In layman's term, how you should interpret that is that uh, you do not have a preferred choice of origin. So the description of the motion of the particle will not change if you choose your origin here or here. Let's say that. Okay. This is another way of saying that there is a translational symmetry because space is homogeneous, and the Lagrangian should be invariant under, should not depend on the choice of origin, or uh, uh, should be invariant under translation like x to x plus epsilon. Okay. Now, if the origin, if the Lagrangian depends on x, then as soon as the Lagrangian depends on x, then in your mind you already have the question with respect to what origin this x is measured. So whenever you see something depending on coordinate, then to define that coordinate you need to have chosen an origin. Okay. Since my system, the description of my system should not depend on the choice of origin, it cannot depend on x. This is my first argument. Okay. So this Lagrangian, whatever that is, a free particle moving in one dimension. So a free particle moving in one dimension does not give me any information about the choice of origin. So that's why I conclude that it should not depend on x. The same thing happens for the dependence of t. The description of the system will not depend on when you start your clock. Okay, so when your t equals 0. So when you start your clock should not alter the description of the motion of this thing. So it means that the time coordinate is also homogeneous. So there is no preferred choice of origin in the time direction. So in actually we just call this thing that my space time is homogeneous. And by the same token, I say that the dependence on time also goes away. All right. Now, the another thing is that if there is only free particle moving through space in one dimension, uh, you do not have a preferred choice uh, of left and right. So in which direction would you choose your positive x-axis? You cannot tell from this. So it's a point particle moving in this thing. So how do you know what is what is right or what is left? Okay. For example, think about gravity. I mean, on Earth in this macroscopic in this microscopic flat space. So in locally Earth is flat. You have a sense of up and down because you have gravity. Okay. So if there were no gravity on Earth, could you tell us, like, so if you are in space, totally like roaming around in space, you do not know what is north, what is south, what is up, what is down. You have no concept. So same is here. Okay. There is no concept of direction. Okay. You are standing on a point and you look, and any direction is the same. Okay. In 3 dimension, all the direction, and this statement is equivalent to this space is isotropic. Okay, so that's why since x dot, the velocity is a vector quantity, it has a directional dependence. uh, to uh, uh, to nullify that dependence on direction, it can only be a function of x dot square. Okay, so that the information of direction is washed away. Okay, so it can, so in 3 dimension, if the particle velocity is v, it cannot depend on v, it must depend on v dot v. Okay, that's why I say that it's a function of x dot square, so that the information of direction is kind of, say, washed away. Okay, because you have no preferred direction. So if you have so if you have only free particle in space, nothing in that, even without knowing Newton's first law at all, without knowing, so I am not appealing to Newton's first law, I am trying to guess uh, the motion of a point particle. And what is the most natural thing I would expect? I would expect space to be homogeneous and space to be isotropic. And from that only, I arrived at the conclusion that the Lagrangian that describes such a system should only depend on x dot square, nothing else, only from symmetry. That's it. Okay. And if you now apply this, then you will see that the momentum is conserved. But that is not all. I can do even more. Okay. So there is another symmetry that I must mention, is the invariance under Galilean transformation. So the invariance under Galilean transformation. Now, what is that? So this is the essential idea. This is the basically the principle of relativity for Newton's law. And relativity. Okay. And so this means that all inertial frames are equivalent. What it means is that you cannot you cannot infer about the state of motion of your reference frame just by looking at physical laws. So in other way, that all the physical laws, all the laws of physics behave in the same way in all inertial frames. So what I mean is that that suppose if you you do any physics experiment, suppose that you are in a train, and you are completely within that train, and you do not know whether the train is moving with respect to the platform or not. And so either the train is moving at a constant speed or a constant velocity, or the train is at rest. Now you want to judge whether that you want to conclude whether the train is at rest with respect to the platform or not, and you want to do physics experiments to do that. So you do whatever experiment you like, say a pendulum hanging from a thread and so on. uh, it will behave inside the train in the same way as it did in the stationary platform. So that's my invariance of physical laws and under the Galilean transformation. So even if the train is moving under at a constant velocity that I will call say v, then then you know that so you have a L of x dot, which is equals f x dot square. So L basically depends on x dot square. So inside a train, the velocity will change. Okay, so the relative velocity, if the train is moving at a velocity v, so it will be f x dot plus v whole square, right? So if it is moving at a velocity v, all right. So of course the Lagrangian changes now, okay. But you know that this change in Lagrangian should not affect my equation of motion. So what I can infer is that this change in Lagrangian should not affect my equation of motion. What I mean by that is that, so this is essentially f of x dot square plus 2v x dot plus v square, let's say. So if this v is small, because Galilean transformation, so this x dot plus x dot v only works when v is small. By the way, I am working in a unit where velocities are dimensionless. So if you like, you just divide it by c. So this v is dimensionless. Okay. So I just say v tends to 0. Now v is dimensionless. Okay. What I mean by that is that you have divided all the velocities by the speed of light, and you are talking about in terms of that fraction of velocity with respect to light. Okay, and that is small. So then I can expand it. So this will be f x dot square plus, this is my change. So you call this thing, let's say delta. So this x dot square plus delta. So this delta times del f del x dot square. All right. Now this delta is of course, if I write clearly, this delta is of course 2v x dot plus v square. All right. Now you can already see that this part can be written as the total derivative of something. So you can write it as d dt of, let me see if I'm doing things. So v x square plus v square t. Okay. So this, right? Yeah, hopefully. So this is already a function of only x and t, only coordinate and time. Okay. And sorry, anyone said something? All right. So I can see that if this thing is a constant, say it's just c, then what I can write is that the change Lagrangian is just f x dot square plus d dt of c times g of xt. Now you already know from lessons of your previous classes that these kind of total derivative does not affect my equation of motion. So my equation of motions will not be affected if the change that is brought in by the Galilean transformation uh, can be recasted in a form such that the extra piece that is added to the Lagrangian can be expressed as the total derivative of something. Then my equation of motion does not change. I have already learned that. And for that, what did I have to do? I had to say that this del f del x dot square is c. So I just concluded that del f del x dot square is equal to c, or f of x dot square is just c times x dot square and nothing else. So the Lagrangian that I was trying to guess is so this is some constant times x dot square. Okay. Now you can recognize that this is just the kinetic energy when this C plays the role of the mass. And remember, did I ever talk about Newton's first law? So I wanted to study the motion of a free particle in 1D, but in 3 dimension it will be the same. You can extend this argument here. And somehow using symmetry argument, I arrived at one of the correct Lagrangian. So this means that this symmetry argument is really powerful. I can play with it. I can have an alternative point of view of nature. So the symmetry perspective gives you an alternative point of view of nature. And if we use our intuition to uncover the symmetries of nature, eventually it will lead us to our correct Lagrangians and the correct equation of motion. Now, there is one subtle thing that I want you to notice here. So when I came to this step, so this is basically a Taylor expansion of the above series. So this only holds when this delta is small or the v is small. Okay. So this argument or this Lagrangian from which I obtained this Lagrangian, okay, relies on this extra velocity that I am writing here being small. So this might not work if v is large, and that gives you right away a glimpse of special theory of relativity, that this kind of Newton's law breaks down when you go to the special theory of relativity. So instead of kind of figuring out nature in the way of Newton, if people at that time had the idea of symmetry and they knew how to arrive at things from symmetry, perhaps the special theory of relativity could have been discovered much earlier than it is. So this way of looking at nature already gives you an impression that something else might happen when v is not tends to 0 and you go to larger velocities. Then this invariance under Galilean transformation will be generalized to something much broader, which is the invariance under Lorentz transformation will replace that. So this only holds for low velocities. So at least I could convince you that this Noether's theorem and these blabbering of symmetries are not in vain. I can get the essential feature of Newton's law just from symmetries. So now I have a very good idea why my linear momentum is conserved, because space is homogeneous. Okay, why my angular momentum is conserved? Because space is isotropic. Okay, so there is a rotational symmetry. There nothing distinguishes from one theta to another theta, and that's why my angular momentum is conserved in the 3-dimensional version, of course. And so this is the power of symmetry. Hopefully this gives you some idea, and I guess I am out of time. Yes, quite a bit. Now tell me, yeah.
So where we have replaced delta by the total time derivative of with respect to d, can you just come to this step?
Here.
Yes, sir. Here, sir, shouldn't it be like 2vx? Because if we differentiate vx square with total time derivative, it should be like 2vx into x dot.
Ah, right, right, right. You are right. So it should be 2bx. So I made a mistake there. Yeah, now it looks correct. Sorry.
Yes.
Yeah, thanks. Anything else? All right then. So let me stop recording now and I will see you tomorrow.